Now let's check how MOSFET is varying according to process. For that I am deleting all these resistors, and we will check the MOSFET. So I am inserting a NMOS and a PMOS. I am using a NMOS with W1 micro, width 1 micrometer and length 0.35 micrometer. I place it here, and the source is grounded, body is also grounded, and the drain is connected to supply voltage. I am using here 3 volt. It is supply voltage is 3 volt. Now I want a VGS for this NMOS. So I copy the voltage source. I am giving a VGS of 1 volt. Okay. So for this MOSFET, the VGS is 1 volt and the VDS is 3 volt. And let's see how much current is flowing. This is not a design, it is just an arbitrary value. Run the simulation. Now also I am doing only the DC analysis. And now we can see the drain current is 36. The drain current is 36.8 microampere. VDS is 3 volt, and VGS is 1 volt. VTH, that is threshold voltage, is 532 millivolt. I am interested in VTH, and in the previous discussion we said the VTH will change according to the process, but not also the VTH, that mu-ins UIX into W by L term, that will also change. So I want to illustrate that also. So for that I am changing this component display option. I want beta effective. Beta effective means beta effective is the mu-ins UIX into W by L term, W effective by L effective term. So I want that term also to be displayed. So I am taking the component display, select the NMOS, and yeah, instead of VD sat, I want the beta effective to be displayed. So you can see now the beta effective displayed, it is 394.8 micro. And again go to the ADE setup model library. You can see the MOSFET is in CMOS TM, that is in typical model. So we put the resistor also in TM. So the options available for us is CMOS WP, that means worst power, that is fast NMOS, fast PMOS. WS is both are slow, that slow NMOS, slow PMOS. W and WZ are one NMOS fast, PMOS slow, and NMOS slow, PMOS fast. This MC is for Monte Carlo, so I am not using that. So now we are using the typical model only. Similarly, we want a PMOS also to compare the difference. So in this schematic itself I am including one PMOS also. Insert PMOS also I am using the same dimension. So for the PMOS also the VDS I am giving the same, and for the PMOS the VGS I want to give 1 volt. So this voltage is 1 volt. So the VGS for the PMOS is 1 volt and the VGS for the NMOS is also 1 volt, and both MOSFETs are in the typical corner. So let's run the simulation. Now you can see the VTH of the PMOS is 0.64 volt, that is 640 millivolt, and the current through that is 8.6 microampere. So this is for typical. So before moving I want to store these values, so I'm using a note to store that. So in the typical model, okay, let's make a table. So I'm making model here and type of MOSFET here, and VTH threshold voltage is one thing I am interested, and beta effective also I am interested in. Beta effective is μnc UIX into W by L term. So we are basically, because of the process variation, VTH and beta effective will vary. So because of that variation the drain current also will vary. So beta effective I am calling it as beta. So in the typical model, MOSFET for NMOS, VTH for the NMOS is 532 millivolt. So I am writing 532 millivolt, and the beta effective we got 394 in the typical model. The same typical model for the PMOS, the VTH is 640 millivolt and the beta effective is okay, beta effective is not displayed here, so let it blank and we will come back and fill that. So let's rearrange the schematic. Go to edit, component display. My intention is to make the display for beta effective for PMOS also. I selected the PMOS and instead of VDSAT I am interested in beta effective. Press OK. Yeah, so the beta effective 120 micro. So beta effective I can write 120 micro, and we can, in the table we can include the current also. For the NMOS the current was 36.8 microampere, and for the PMOS it is 8.6 microampere. So this is the case when both the NMOS and PMOS is in the typical model. Now let's change the model and see how much all these parameters are varying. So in the setup model library, instead of typical model, I am changing this to WP. That means worst power, that is fast NMOS, fast PMOS. WP means worst power, that is fast NMOS, fast PMOS. Press OK and run the simulation. You can see the threshold voltage of NMOS is decreased to 348 millivolt and the beta effective is 534 micro. In the typical corner, the threshold voltage was 532 millivolt. Now the threshold voltage decreased to 348 millivolt. The beta effective, that is mu1 COIX into W by L term, was 394. Now it has increased to 534. So VTH is increasing and mu1 COIX, that term is increasing. VTH is decreasing and that mu1 COIX term is increasing. So effectively the MOSFET speed will increase and the current through the MOSFET will also increase. The same thing happened for PMOS also. If you observe, the threshold voltage initially was 640. Now it is decreased to 494 millivolt. And the beta effective value, initially it was 150. Initially it was beta effective was 120. Now it has increased to 151.7 micro. As a result, there is variation in the current also. Initially the current in the PMOS was 8.6 microampere. Now it is almost doubled. So the new current is 19.78 microampere. So we can add these new values also into the table. So the worst power, that means slow NMOS, I am writing yes NMOS. Now the new VTH for the NMOS is 348 and the new beta effective is 534 and as a result the current increased to 92.53 and the same in the WP corner for PMOS. Okay, sorry, this is not slow NMOS, this is fast NMOS, sorry for that. And here the PMOS is also fast PMOS. The threshold voltage is decreased to 494 millivolt and mu1 COIX into W by L term, that is beta effective, is 151.7 millivolt now, 151. As a result, the current increased to 19.78 microampere. So this table we can use for the comparison of these values, and now we did the simulation for the worst power corner, that is fast NMOS, fast PMOS corner. Now let's do the worst speed corner, that is slow NMOS and slow PMOS. So in the model library you can change the model name from WP to WS. Okay, save the schematic and run the simulation again. Now you can see, observe for the NMOS. For the NMOS, the VTH has increased to 619 millivolt, that is 619 millivolt. So in the typical corner the threshold voltage was 532. and in the fast NMOS corner, that is WP, in the fast NMOS corner it was 348, and in the slow NMOS corner it is near to 620 millivolt, that is 619 millivolt. So we can edit our table now. In the worst speed, that is slow NMOS and slow PMOS. The threshold voltage is 619 millivolt, and beta effective is 290. Beta effective also decreased considerably, so the speed of the device and the current through the device also will increase. The current through the device is 17.17 microampere only. So you can see the typical corner, all the values are in the middle range. Threshold voltage is 532 millivolt in the typical corner. In the worst power corner, that is fast NMOS corner, it decreased to 348, and in the slow NMOS corner it increased to 619. For the PMOS also the case is similar. The WS corner, that is fast it is slow PMOS. The VTH is increased to 806 millivolt, and the beta effective is decreased to 84.96 micro, and the current also decreased to 2.03 microampere. So from this table you can see the variation, the maximum variation. This table represents the maximum variation of the VTH, beta effective and those parameters because of the process. So the two corner remaining is fast NMOS, slow PMOS, slow NMOS, fast PMOS. For the fast PMOS, slow NMOS corner, the PMOS will be of this parameter. PMOS will have these values, and slow NMOS, then NMOS will have these values. So let's see that. Check the schematic, save the schematic, and set up. Change the model library from WS to WO. Run the simulation. You can see in this corner, so in the WO corner, the NMOS threshold voltage is 342 millivolt. So 342 is near to this value. So in this corner NMOS is fast. So this corner is fast NMOS. So fast NMOS, slow PMOS. Let's see the threshold voltage of PMOS here. Threshold voltage of PMOS is 809. So it is close to this SPMOS value. 806 we got for slow PMOS in WS corner. I am not adding them into the table because these are just combination of the two things, that the two extreme corners that we have seen earlier, that is slow NMOS and fast NMOS, fast PMOS, slow NMOS, slow NMOS. Now the combination is coming from fast NMOS and slow PMOS. So the values are very close to what we got earlier for the slow and fast MOSFETs. Now let's do the last corner, that is WZ worst zero corner. So in this corner we are expecting a slow NMOS and fast PMOS. In the WP corner both were fast, in the WS corner both were slow. In the WO corner NMOS was fast and PMOS was slow. So now in the WZ corner NMOS will be slower and PMOS will be fast. So the threshold voltage of NMOS is 617. It is near to 619 which we got for slow NMOS. So this corner is also slow NMOS. And for the PMOS the threshold voltage is 484. It is near to what we got for fast PMOS. So this is a combination of fast PMOS, slow NMOS. So when we design a circuit which involves NMOS and PMOS, we can expect this much variation for the threshold voltage. So by these simulations we saw how much the characteristics, properties and characteristics of the MOSFET changes with process. So as we said for the resistors, when we design a circuit which involves NMOS and PMOS, we have to make sure that it is working properly across all these corners. If it is working for only typical corner, then there is no guarantee that when we make an IC it will be in typical corner. It could be anywhere in between all these four corners, this WP, WS, WZ and WO. So when you make a MOSFET in real world, in real IC, real silicon, it could be anywhere in between these corners. So the process corner variation is equally applicable to capacitor also. I am not doing in the simulation, but we can see the two corners as we saw in the case of resistor. We saw in the typical value the resistor was a particular value, and for the worst power and worst case and worst power and worst speed means minimum resistance and maximum resistor corner. Like that the capacitors also have two corners. It has a minimum corner and maximum corner. So accordingly it is called WP and WS. I am not showing the simulation for capacitance. You can do that, and in the ADE you go to setup, model library. Here the capacitance model, it is typical now. You can click on that. So in the capacitor you can see it is WP is there. Worst power means minimum corner for the capacitance, and worst speed is capacitor will be higher than the typical value. So this is the maximum capacitance. Okay, and restore this to typical model. And till now we were doing for the individual devices. Now we will do the process corner simulation for circuits, how it is varying with respect to process corner. Let's do the just do the inverter transfer Cara for this inverter. I am deleting the second inverter now. Now I am doing the transfer Cara. For that I am labeling this as V underscore V in, and I am connecting a load capacitor. Ideal capacitor I am connecting because I am not interested in the variation of that capacitance now. So I am connecting a capacitor from the analog library. Assume it is 500 femtofarad. It is the load. I am labeling in and out to these two nodes. And now I need a DC sweep of the input, and I want to see how much how the output is varying. Select a DC sweep of component parameter, select the component, I want the input and the DC value of the input. Select OK, and the DC value of the input I want to start from 0 to 3, and sweep type I put automatic. Okay, then I want output to be plotted, input and output I want to plot. Save the schematic and run the simulation. See, now we got the transfer cara in the typical model. See, go to the setup, and the model library that we see is in the typical model. So now I want to change, I want to see how much this transfer cara is varying according to the process. So for this this circuit involves only NMOS and PMOS. The capacitance is the load, so I am not considering it as a part of the circuit. I am interested in the inverter. So I want to check all the 4 process corners in the inverter. So till now we were doing the process corner simulation by selecting each and individual corner by going to the model library and changing here. So if we do like this, we can do only one simulation at a time, and we can check only one corner at a time. So we have another option in Cadence. We can have process corner simulation in ADE XL. So before going to ADE XL, I am saving the state so that I can use this simulation state there. Session, save the state. I am saving it as state 1, or okay, transfer cara. Okay, save underscore transfer. I saved it. Now save the schematic, go to ADE XL, create a new view, press OK. Now we got ADE XL. ADE XL is a powerful tool. We can do all type of simulation here, like process corner and Monte Carlo. All this we can do. So in this column, the data view column, we have test, global variable, parameter and corner. So first of all, we have to select our test. So add a test, and our schematic is process underscore corner. Select that, and we already saved the state in the name of state underscore transfer. So if we already saved the state, we can just load that state here. So I just loaded the state. So I repeat the step. We open this ADE XL and we add a test. Since I already saved the session, and so that I get all these simulation setup and those in ADE XL. Now I got I have a test here. Initially I had no test. Now in the corner, now it is only nominal corner. So before doing any other simulation, just do one simulation in the nominal corner. Nominal corner means all are in the typical. So we got this output. So this is in the nominal corner. Now add one more corner here. So in the corner setup, we have temperature. See, this temperature is a very important parameter, but I didn't discuss that in this simulation because we were discussing only on the process variation and process corner. But when we do the simulation, when we do the process simulation, this temperature corner is also very important, because almost all the parameters in the circuit vary with temperature. So the temperature is a very important parameter in the corner simulation, but here I am not including the temperature because I am only concentrating on the process parameter. So here in the model files, I want to add the model. One window will pop up. Import from the test. So you got all the models here. So here I am not interested in the resistor, capacitor, bipolar, so I can deselect all them. In this schematic I have only MOSFETs. If you had some capacitor or resistor on those things, then you can include all these models and press OK. So now I have only MOSFET. Here you can see all the corners, like typical corner, WO, WP and those things. So I selected the WO. This typical model I am deleting. I selected WO and press this button. Now a new corner is added here. Nominal corner was there. In the nominal corner all was typical. Now I created a new corner named C0. Everything is typical, but the MOSFET is in the WO corner. So I want to add one more corner with WP, and I add it, and I am adding all the four corners. Now add WS and WZ. So C0, C1, C2, C3, we have all four corners for the MOSFET. And if you had capacitor and resistance, you can do the same for capacitor and resistance also. So press OK, and you can see here we have one sweep, that is we are sweeping the input voltage, and we have four corners. These four corners is for the MOSFET four corner that we selected here. So now run the simulation. At a time it will run all the four simulation. And it will show the result of this simulation after the simulation. You see, the input voltage is same, it is for all the corner, because we are giving it with an ideal voltage source. But you see the transfer cara is changing with respect to process. So the green one which I selected now was the typical corner, and all the other four corner the transfer cara is changing. So this is an example for how you do the corner analysis in Cadence. So one more example we can do. I'm closing this. One more example I want to do in transient domain. I delete this. Delete this from here. I copy the stage. So now it is a two-stage two inverter chain. I increase the capacitance value to 1. Okay, let it be 500 femto itself. And the NMOS size I want to increase the driving capability of the MOSFET. I made this to 4 micrometer width, and for the NMOS size I made 2 by 0.35 micrometer. So instead of a DC output, now I am giving a pulse waveform with DC, no DC voltage, but I want the VDC changed to V pulse. So voltage 1 I want 0, voltage 2 I want 3. The pulse period I want 100 nano, or let it be 500 nano. Delay time, rise time I want 10 nano, fall time 10 nano, and pulse width 200 nano, or you can use 240 nano. I want a transient simulation now. I want to run for 500 2 microsecond. I want to and I want to plot output to be plotted. I want the input and the output to be plotted. So run the simulation. And you can see this simulation is for the typical corner. I'm increasing the load capacitance to 1 picofarad, and run the simulation again. Before that, I want to decrease the rise time to 2 nanosecond, and this also to 2 nanosecond. Check and save. Run the simulation. Now for the typical corner we got this the red curve is the input and green is the output. Now this is for the typical corner. Now I want to do the process corner simulation. I want to see how this is varying with process. So I am saving this session, save state. Now I am calling it as state underscore. I am naming it as transient. Okay. Now I want to launch ADE XL to do the corner analysis. Okay. So all the 4 corners that we did earlier is still here, so we need not go and edit the corners. If you want, you can click here to add one more corner. Let's add one more corner of temperature. I want to add a corner with temperature minus 40 degree and a corner with 150 degree. So 2 corners are added here, but here one issue is there, because all the MOSFETs is in the typical model, and for that corner we added these 2 voltage. In the typical corner we added 2 corner for the temperature. Now if you want for the other corner also you can add. For that you can select here in the MOSFET. So I want to do a simulation with MOSFET in the worst power and with the maximum temperature. So 150 degree temperature I am giving, and the MOSFET I want to be in the worst power corner. So I created one more corner here with the temperature 150 and MOSFET in worst power. So let's add one more corner with very less temperature and very slow corner, WS. So I added one more corner with temperatures minus 40 and worst speed corner is added. So you can have all these combinations. So before making the chip you should run all the combinations of temperature and all the process corners, and press OK. Now we have a lot of corner, not lot, but we have 8 corners now. Let's run the simulation. You can see the status here. We have total 9 corner including the nominal corner. You see, this is not the graph what we expected. It is actually plotting the previous setup. Earlier we were trying the transfer, we are plotting the transfer Cara. Okay, it is not plotting the transient analysis, it is still doing the DC analysis and plotting the transfer Cara. You know what is the reason? The reason is we didn't change the test here. The test we did was the earlier one. For example, you can open the test and see the test. It is still the DC SIP we were doing. See the automatic 0 to 3 V in DC SIP we are doing the DC analysis. So we want to change this. So you can go to session and load state, and this is the new one, state underscore transient. Select that. Now the test has changed. Now if you run the simulation, you will get the corner analysis for the transient response. So don't forget to change the test here. So if you want, you can add one or more test here. So the corner simulation will do, you can do parallelly for transient and DC value you can parallelly do. If you want, you can add one more test here. I'm not doing it now, just running the simulation for the transient. You can see the status here, total 9 simulation, 8 corner with 1 nominal corner. So now it is the transient response. If you zoom, you can see this variation. This is the same W by L for all the MOSFET, but only the variation is the process parameter. This curve, this straight line curve is the input, and all this variation that you see is in the output wave. So this variation is happening due to the process corner. So when you make an IC with this inverter chain with this W by L, so you can expect any of this wave, any of this curve you can expect. So I'm stopping the this tutorial here. So we discussed the process variation and what are the reasons for process variation, and we saw individually the process variation in resistors and MOSFETs, and then we simulated the process variation in two methods. One by individually going to the setup and model library and changing the model. So in that method you can do only one process at a time. Then if you want to do a lot of process at a time, you have to open the ADE XL and to do the corner simulation in ADE XL as we demonstrated now. So I am stopping this tutorial here. Thank you for watching.